entropy. Now, entropy is kind of a way to think about it is as saying it's disorder or randomness. Now, when you get to college, your professors are going to tell you that I taught this to you wrong. Okay, so not a perfect definition, but to be honest, this is a perfect definition for you where you're at right now. The way I describe entropy is always with a jigsaw puzzle. I told you at the beginning of the semester that I love working a good jigsaw puzzle. And I spend hours putting all the pieces together. And it takes me forever to do that. Once all the pieces are together and it's beautiful, what will happen to that puzzle if I try to pick it up? It took me hours to put together. If I try to pick that puzzle up, all of a sudden all the pieces will come apart in an instant. That gives me a good analogy for entropy. Where's the entropy high? Remember, entropy means disorder. Where is a lot of disorder? When the puzzle's put together or when they're in all their separate pieces? Definitely more entropy when the puzzle's not put together. Less entropy when we put it together. So the more random, the more disorder present in something, the more entropy it has. Now, a concept, this is actually a law, is that generally speaking, entropy in the universe is increasing. As a whole, the whole universe, entropy is increasing. Think about it. What happens to things over time? They wear down, they break, they get ruined, they have to be replaced. That's entropy. The longer time spent, the more random, the more disorderly things get. So that is exactly why this is the way it is, and it is the law of disorder. It's actually one of the laws of thermodynamics. Very important concept. Now, entropy is a way to describe energy, so its unit is also joules, just like all of our other energy words are. Okay, so what you're going to have to do with entropy is you're going to have to take something, the process, a reaction, phases of matter, and determine which one has the most entropy. So let's have a look here. We're thinking about which one's the most random, which one has the most disorder, and that's going to have the more entropy. So we think about it. Which one has more entropy? Increased temperature, or increase in the temperature, or decrease in the temperature? Okay. You remember, temperature is directly related to kinetic energy. The higher the temperature, the faster the particles are moving. The lower the temperature, the slower the particles are moving. Which is more disorderly, moving quickly or moving slowly? Definitely increasing temperature. The faster the particles are moving, the more disorder there is present, the more entropy. Okay, which one has more entropy, the reactants or the products? Okay, the first thing you should always look at is the states of matter. And I'm going to talk to you a little bit more about states of matter in just a second. But they'll give them to you. Gas, gas, gas. So we have all the same state of matter. So we can't look at that, okay? But always start there, because if they have a different state of matter, that's what's going to give you your answer first and foremost. Instead, we've got to look at jigsaw puzzle versus pieces, okay? So count the number of molecules on either side, or the number of particles. This side has 2. This side has 3 hydrogen and 1 nitrogen. So do you see that this side has 2 particles and this side has 4 particles? So which side has more entropy? The side with more pieces. This is like the puzzle, whereas these are the pieces individual. So that definitely has more entropy. Ice, water, or steam. Now we're going to talk about states of matter, okay? Ice is a solid. Water is referring to the liquid water. And steam, I don't love that it uses that word. It should say water vapor, because technically if you see steam, technically you're seeing condensation, kind of like a cloud. When you see gas, water, it's really not a gas, because water's clear. But whatever, they're referring to here, they're referring to water in the gas phase. Okay, I want you to think back when we simulated those particles. Here's what a solid particle looks like. Remember, they're real close together and they're just vibrating. Here's a liquid, free to move. A gas, so really far apart, moving really fast. Do you see that This one has the least amount of entropy because they're real close together, they're structured, they just vibrate. This one has more entropy because they're free to flow around in random ways. This one by far has the most entropy. So anytime you're given a reaction that has different phases of matter, go with this first. Solid has the least, gas has the most. So steam has the most here. Okay, let's look at these over here. Predict the sign of delta S. S, by the way, is the way we describe entropy. So capital S refers to entropy. And delta means change. You saw that in the gas law unit. So that means change. So change in entropy, okay? If entropy is increasing from the reactants to the product side, delta S will be positive. If entropy is decreasing, delta S will be negative. So you need to look at the reactants versus the products. See if it's increasing as it goes across, or if it's decreasing. So does this have less or more, okay? The first thing you should look at is the states of matter. If we look at this first one, gas, gas, gas. So the states of matter is the same on all of it. So that means we can't look, that's not going to give us the answer. When the state of matter is the same on all sides, on all substances, that's when we start looking at puzzle versus pieces. This side has 2 particles. This side has 1 particle. So do you see how the reactant side actually has more entropy here? So do you see how as this reaction goes to completion, entropy decreases? So delta S would be negative in this case. Okay? Okay, now let's look at this one. Gas versus aqueous. That's the only state of matter I haven't talked about. So I'm going to put that right here, and I want you to copy this in your notes. I'm going to put it in a different color. So the least entropy, we agree, is solid. Okay? Then we have liquid. Okay, now do you remember what happens when a liquid mixes or a solid dissolves in water? Do you remember how solids separate, especially if it's ionic, will separate into its individual ions to become more particles? So that one definitely has, aqueous is definitely more than solid. And you know when you put a liquid in, when you first put it in, it's mixed together with itself, and the other liquid is mixed together with itself. But once you combine them, they get jumbled up, and all of a sudden they're intermingling with each other. So definitely mixing them together would be more. So aqueous is here, but less than a gas. Because a gas is going crazy, the particles are going like this, and then when they dissolve, they're trapped in that liquid. They still are free to move around, but nowhere near as much. So here's the order. Gas is actually the most entropy. Kind of running out of space there a little bit. But that's what you need to know. Solid is the least, gas is the most, and aqueous fits right between liquid and gas. So now when we look at this, as we take ammonia in the gas phase and force it to dissolve, this is actually less entropy here. This one has more. So therefore, the change in S is actually negative. Okay? Now, this one's going from liquid to aqueous. If we look at our phases, liquid has less, aqueous has more entropy. So this would be the most. So in this case, this one has less entropy, this one has more. So as this reaction is taking place, we're increasing entropy. Then we look here, the first thing you should look at is the phases of matter. We've got liquid to solid. Okay, so we're going like this as a liquid, and all of a sudden, it starts looking like this. You see how entropy's gone down. So this one has more entropy, therefore entropy is decreasing. Now let's look back at our law of disorder. Entropy in the universe is generally increasing. That's the direction we want to go. Things break. I drop a glass of water, the glass shatters. But would you see potentially all that glass coming back together and all of a sudden it being on the counter again? No, it's not how our universe works. So generally speaking, entropy in the universe is increasing overall. That doesn't mean every reaction will result in increasing entropy. It just means that generally that's more the direction our universe wants to go. So of these 4 reactions, which is the one that's most likely according to our law of disorder? Yeah, definitely this one, because entropy is increasing here. That's really what the universe wants to be doing over time, whereas these 3 are kind of going in the reverse of what the universe would generally want to do. So there you have it. That's entropy.